Hello and welcome to today's webinar, How to Choose the Right Database for Your Workloads. This event is produced by Actual Tech Media and presented in partnership with our friends over at InfluxData. Thanks so much for being on the webinar today. This is going to be a really cool event, especially if you have data, and most of us do, and you're wondering exactly what to do with that data. We're going to learn a lot on that topic today. And before we get started, there's a few things that you should know about the format of today's event. I should mention first off, my name is David Davis of Actual Tech Media, and I'm glad to be serving as the moderator. As always, we want these events at Actual Tech Media to be educational. We're all former IT professionals ourselves here at Actual Tech Media, and we know how tough it can be out there in the world of technology to find solutions to your challenges, to find answers to your questions, and that's what this event is all about. So we encourage your questions there in the questions box of your audience console, and we'll be doing a Q&A session at the end of the event. We even have a best question prize to help maybe further encourage those questions or shake some of those questions loose. I'll talk about that here in just a moment. But first, I want to call your attention there to the Handouts tab. It's there that you'll find a link to the InfluxDB Cloud, the #1 time series database out there in the market today. So if you just click on the view button on that link, that will open up a new web browser tab or page in your web browser, and you can check that out during the event or after the event. And it's free to get started, I should note, free to get started with the InfluxDB Cloud. So we'll have that event or have that link up there the entire time during the webinar. You can check it out anytime that you'd like. And then also at the end of the webinar today, I'll be announcing the winner of our grand prize on this webinar. If you are attending on demand, watching a recording after the fact, of course, that drawing has already occurred. The prize drawing for today is for an Amazon $300 gift card. And then, as I mentioned, we also have our best question prize. For an additional gift card, an Amazon $50 gift card, you must ask a question to be entered into that prize drawing. And all prize winners on the event, of course, must meet the Actual Tech Media prize terms and conditions that you can find right there in the Handouts tab. All right, so with that housekeeping information out of the way, I'm excited now to bring in today's expert presenter. Welcome to Charles Mahler, who is a technical writer at InfluxData. Our expert presenter today. Charles, it's great to have you on the event. Take it away.
All right. Thanks for the intro. Well, let's jump right into it. So basically today, we're just going to go over kind of the database ecosystem and some of the things you should consider when choosing what database to use for your application. So the agenda, we're going to look at kind of some trends that are active right now, what we're seeing, what kind of the different types of databases available. There's a lot of them, a lot of specialized general purpose ones, and we're going to look at the trade-offs involved with some of those different types of databases. And we're looking at the future of databases, some new features, some new, again, trends that looking forward, how it might impact you as a developer and impact like the projects you're working on. And then finally at the end, we will have that QA set, some time set aside for QA. So before I even start, I think it's important to kind of keep in mind, first of all, like there's always new technology being hyped up. So I think it is important to like not fall for the hype. And when possible, you should just keep it simple. There's also nothing magical, like early days of NoSQL, these new types of databases, there's a lot of promises made. And in some cases, they didn't live up to the hype and it kind of burned a lot of people. So there's no magical technology really. When it comes to computer science, there's always some sort of trade-off. So it's always good to have that in mind. Again, for simplicity for this presentation, you can't really go into the weeds too much on all these different types of databases. So a lot of them will obviously have some overlap with each other. So if you see like a certain database I've categorized in like one specific type of database, there probably can be used in other areas. I just kind of simplified it for the sake of this presentation. So here are the types of databases we'll be covering today. So kind of you see different types and some that have some crossover, multimodal, that sort of thing. And we'll get to those in a little bit. But to start, so the current database landscape. So again, as you can see, this is according to DB Engine's basically the market share for each type of database. So obviously NoSQL gets a lot of hype, but as it stands, you still have relational databases by far like the most popular and kind of dominant just in terms of being used with applications. But you can see that some of these NoSQL databases are starting to kind of chip away at that over time. So you have document, you have graph, some of these other specific types of databases that are gradually kind of eroding that dominance of the relational database. And then if we look kind of drill down, so that last slide was like the present, where it's about 71% of databases are relational. But if we drill down and look at like the actual trends, we can see that the fastest growing type of database is time series database. So that's, I work at InfluxData. That's our kind of type of database. And we also see key value and graph databases are the second and third fastest growing. And you can see that if you look at that red line, the relational database, you can see it's actually below, which means it's kind of getting chipped away at slowly. Obviously, as it stands, if we looked at a snapshot of time right now, relational is dominant, but we can see that businesses and developers are starting to see the value of these new types of databases. So I think it's important as a developer to kind of, you don't have to jump in on the newest thing, but it is good to have like a kind of a keep an eye on trends. And when you start to see something big, a big shift happening, it can be good to be kind of on top of things. So what actually makes databases different? What separates like a relational database from a graph database from a document database? So really like at the core level, at the architecture level, these are some of the things that go into designing a database and some of the things that people you have to think about when it comes to these performance trade-offs. So first off is like, how are you actually storing that data on disk? Like how are the zeros and ones organized on hardware? So they can be row-based, they can be column-based in terms of storage, and that will have a variety of implications for how your database performs. Then have to look at your indexing structure. So you have to think about things like the primary index, which is like right now mainly B tree versus LSM tree, which we'll go into in a few slides. Then you also have to think about your secondary indexes. So certain data points, like if you have a specialized something with like geographic data, you're going to have an index that will perform better and is optimized for that type of data. So a lot of these that we're going to look into, they'll have some primary index, and then they'll have a specialized secondary index to optimize performance for their specific workload. You then have disk-based versus memory-based. So you have databases like Redis that only, they don't really worry about persisting data to disk. And that gives a bunch of kind of performance boosts because they don't have to worry about trade-offs. They just kind of throw away a set of problems and tell you to deal with it using another tool. But the result of that is that they can really optimize for their use case. So choosing between, are you going to worry about persisting data to disk? Or are you just going to focus on working with data in memory? You have to think about the trade-offs of compression. So you can go from maximum compression on disk, which is obviously going to save you storage. But then you have to think about the encoding and decoding of that data, which could have performance implications. So some of these new databases, they actually trade off in some situations. They'll prefer having more, basically the same data taking up more space on disk, but they do that because the compression algorithm, it gives them better performance in terms of pulling data off disk. They don't have to spend as much CPU or other resources converting and moving that data back and forth between formats. A lot of databases now, you get that separation of compute and storage, and you also get kind of hot versus cold data. So you can optimize for cost and performance by, if you have data that you very rarely access, you put that on cold storage, a cheaper form of storage, and you don't bother with like keeping it in RAM if you rarely ever access it because it's much more expensive to do that. So databases are getting smarter about how they kind of transfer data between memory, between disk, between like even object storage for like cold, long-term like archival of data. And finally, you have the trade-offs of durability, recovery, kind of consistency, where you can trade off, like if you're familiar with CAP theorem, you can make a lot of trade-offs depending on your workload. If data doesn't need to be 100% consistent, you can get a lot of performance gains by dropping some of those guarantees. So how do you actually choose the right database? We talked about, so those were like the trade-offs, the thoughts that go into actually making it. So then once you know about those, how do you actually kind of choose which one? So primary above all else is thinking about how you actually access your data. If you make like a kind of a typical web app, if you think like Twitter or Facebook, the majority of their data is going to be querying of data. For every, like you think about like some celebrity creates a tweet, that's one write to the database, but potentially millions or tens of millions of people are going to be essentially accessing that data. So that's a very read heavy workload. And there's different things you can do to optimize for that. On the other hand, you have like time series workloads like monitoring, IoT type stuff where potentially you have sensors that are writing together millions of data points per minute, per second. Um, that's a completely different kind of way that the database needs to work if it's going to be accepting millions of writes per second. And that data could also be accessed in different ways. Like instead of wanting one data point, you might want to query across a range based on time. And other, like a graph database, you're going to be wanting to access nodes of data in different ways as well. So um, really the thing above all else before you just choose some database because a lot of people are talking about it, think about really like how you're actually going to be accessing your data, because what it comes down to, that's all a database is. It's the trade-off between reading data and writing data. Like the fastest way to write data is you could just append every new data point to a file. That's going to get you pretty much the best performance possible in terms of writes. The downside of that is to find that data again is you're going to then have to do a full scan of the entire data set. So it's a trade-off between write performance and then indexes to make queries faster. Again, you also have transaction isolation. So like relational, you have your ACID guarantees. So if you're doing stuff where you really need consistency and you need reliability for transactions, that's going to take a hit on performance, but it might be a requirement. On the other hand, if you know your workload doesn't really require that, you can drop those guarantees and you can get much better performance in other ways. You have scalability. If you know ahead of time that you don't need horizontal scaling, you know, like at most we're gonna have this much traffic, we can just vertically scale it. Then that's really something that you shouldn't bother worrying about. Don't worry about sharding and horizontally scaling your database. If you know that at max, like an internal tool, there's going to be 100 people using this. Don't overthink it. Just go with the simpler solution. Business stage is another factor. So a lot of the kind of proponents of NoSQL databases will say that like most of them being schemaless, it gives you a little flexibility. So if you're like in a MVP stage or it's a side project or you're prototyping, having that flexibility, not having to commit to a schema ahead of time has a lot of benefits. And then finally, in-house knowledge. If you're going to retrain your whole team on a new technology, make sure it's worth it. On the other hand, sometimes it just makes sense if you have somebody who's, or a couple people who are experts in a certain type of database, it might make sense just to stick with that rather than trying to retrain your whole team. So it all comes down to really just doing what makes sense for your business. So before we go into like the specific databases, we'll just go high level, kind of the standard relational versus NoSQL. And what you'll see here is that like while it's kind of classically broken down, you will see that in a lot of cases, a relational database is actually more similar to a what's defined as a NoSQL database. Like their use cases have more overlap than with like a graph database versus a document database. So this really isn't the best way to um, kind of define databases, but this is kind of the classical way of doing it. And broadly speaking, a relational database is a B tree type index. And what that is really optimized for is read performance. And even more so, it's optimized for their design in the 70s. If you think about it, relational databases, back then RAM was very expensive. So they just assumed that the majority of queries or a good chunk of queries are going to have to hit disk. So the B tree is all about minimizing those queries to disk and minimizing the number of seeks that your database will be doing. Um, Obviously, you have your table-based structure, your defined schema, and with that, you have your ACID guarantees. And the primary way to scale a relational database, the easiest way, is going to be vertical scaling, just getting a bigger server, more memory, bigger disk. They weren't really designed with horizontal scaling in mind, although there is quite a few tools now that enable that, but out of the box, it's going to be a lot harder to horizontally scale your database. So for NoSQL, they're generally speaking, they have LSM tree, which is a different type of index that gives a lot of benefits for write throughput, but there's obviously some trade-offs as well. It's not a perfect, it's definitely more modern, but it's not perfect by any means. You have multiple types of storage. Um, we'll go into some of these models. You have document, you have graph. It's not just table-based. Most of them are going to be flexible in terms of their schema, although some do allow you to kind of define it as well. The consistency trade-offs, it's like the buzzword is they call it base, but that's really not a great way to go about defining it because all these different databases have different trade-offs. And if you want to look into that, you can look into kind of CAP theorem and some different ideas around this. But when it comes to like a distributed or horizontally scaled database, um, a lot of the benefits that you get from that, you have to trade off on consistency. Although some like MongoDB and some other ones, they have added back, they realized that for certain use cases, you need that. And if they wanted to appeal to certain developers, they had to add those. And finally, you have your horizontal scaling. So most of these out of the box will include some sort of solution, some sort of way that makes it really easy to scale horizontally. And a lot of them were built from the ground up with the idea of making it easy to scale horizontally in mind. So the first category we're going to look at is going to be our relational database. So basically, as we covered, stored relational model stored in a tabular format on disk. The representation is like a single row. It's going to be right next to each other sequentially on disk. And generally speaking, you're going to be using SQL to access that data. And the prime examples of this is going to be Postgres and MySQL. So the pros and cons of this is that it's very solid performance across a broad range of applications. You can use it a lot of different ways. Biggest thing probably is the ecosystem. They've been used in production for decades. They're battle tested, and there's a lot of tools for like managing them. Pretty much anything you need, anything you could think of, somebody else has also thought of it. They've already made a tool to make it easier. So that's a big benefit. And then data consistency, ACID transactions, all that stuff we kind of talked about before. Con-wise, you have the biggest thing would be like the struggle with write, like high write volume. That's pretty much the reason that the NoSQL kind of paradigm came about. Is you had companies that we'll kind of talk about, like Amazon, Google. They were struggling to scale writes to these relational databases, and so they came up with, like, by the time they horizontally scaled it, sharded it, done all these different tactics to try to scale their horizontal database, they'd already lost a lot of the benefits of a relational database. So they realized, let's just create a new database that upfront we know the trade-offs we're making, we know the downsides, and then we can plan around that. So use cases, pretty much, it's gonna, at least for starting off low scale, it can be used for almost any type of application. And obviously any application where you need those ACID transactions, like financial, anything where you don't want to potentially lose data, it's ideal for that as well. So key value databases, to start, probably the most simple type of NoSQL database, because you can think of it as basically just a hash table or in your programming language, and it's just persisted to disk. That's kind of how you can think about it. It's a key that maps to a value. So it can be, it's effectively like in the conventional key value database, there's no structure to it. You can just throw like really any blob of data into that database. And as long as you have the key, you can access it and do whatever you want with it. So the original paper that inspired a lot of these open source ones would be Dynamo by Amazon. But then as far as open source databases go, you have Redis and you have Riek as well. So the basically pros are that you're going to get amazing read and write performance just because it's not doing a lot. There's really no indexing going on. So there's not a lot of overhead when it comes to writing that data. You're also going to get great read performance because it's basically a lookup. Like you have the key, it maps to it, and you just get, there's no scanning really of your table, of your database. It just grabs it. And flexible, it's about as flexible as you can get by default. It's literally just a key mapping to some sort of data. And as a result of that, it's very horizontally scalable out of the box. Downside is going to be weak consistency. Most of these types of databases, that's the trade-off they make, is that, like, for example, like if somebody writes a new data point, updates a key value, it might take time for that value to propagate to other nodes. So in theory, you could get a situation where somebody updates a value at the same time somebody makes a query, and they get like it'd be called a stale kind of data point. So in some cases, if you don't want that potential to happen, a key value database doesn't make sense. The other downside is that by default, like the kind of textbook key value database really has no way to query data. Like if you don't have like beyond the key, there's no real built-in way. Some of these other databases over time have added some different types of queries and some secondary indexes, but like kind of the textbook key value database, there's not much you can do in terms of querying capability. So the standard use case, or like the kind of classical example, is Amazon put out their paper on Dynamo, and they used it initially for their shopping cart because around holiday season, Black Friday, Christmas, they were having tons of trouble scaling their relational database, and they're having lots of issues with carts not getting updated, with orders failing. And they realized that by the time they've denormalized their data, by the time they've done all these different strategies to try to scale their relational database, they had lost all the benefits in terms of consistency and stuff anyway. So they realized, let's just make this NoSQL, or what became the concept of NoSQL, where we just know up front that we're going to lose consistency. We know up front that we're going to lose this other stuff, but we get the scalability, and we can plan around like the downsides, that you can just preemptively plan around those. So the shopping cart is kind of the prime example, but you can also use them for real-time, pretty much any type of real-time feature where you need to update and write data in high volumes. And then you can also do stuff like personalized recommendations, session management. So document database is kind of an extension of your key value database. It basically takes that concept and then adds a little bit of metadata, or gives you the option to add metadata, and essentially kind of like format it in a way that makes sense to you, that makes sense for your use case. So it'd be classified generally as like a semi-structured data. Benefit of this is that you get data locality. So on disk, all that stuff, like instead of having to do a join to grab data that you might need for like a user profile, you can just store all that information in a single document about a user. And then when you're reading that, like in terms of off disk, it's all sequentially next to each other. So you get a performance benefit there. Prime example of document database as far as open source goes is going to be MongoDB. Pros and cons, you get the flexible schema. Performance is pretty similar to like a key value database. From a developer productivity perspective, you also get the benefit of, it's in many cases a lot easier to map your concept of how your data is formatted to a document database, as opposed to trying to make it fit into the relational kind of table structure. And then scalability is, again, most of these are designed from the ground up to be horizontally scalable. Downside, again, consistency, depending on which database you're using and depending on kind of how you configure that. Like Mongo, for example, has the ability where you can kind of opt in for ACID if you need that. One downside is also like the relationships between documents. If you do find yourself in a situation where you end up realizing, oh, these documents, we end up needing to query these together, that can be a situation where you would have been better off just going with a relational database. Like if you end up having a data schema where like you end up just querying two documents together all the time anyway, like you're just taking a performance hit, and you probably would have been better off using a relational database in that case. So I'd say, in my mind, document databases are probably the most similar to relational databases in terms of they're very general purpose. You can use them a lot of different ways. And as far as like a startup is concerned, they're also a big benefit there. They're used a lot there because you can iterate pretty rapidly, and you don't have to worry about migrating database schemas and stuff like that. So now to time series databases. So as the name implies, it's designed for working with time series data like IoT sensor data, monitoring data, pretty much, or just events, like anything in your application. If you've done anything with like event-driven architecture, it could also be used for that. Like this event happened at this time. That's the kind of thing these things are optimized for. And as part of that, what makes them kind of interesting is that we'll cover like analytics type databases in a little bit. And the interesting aspect is that these databases, by their nature, they have to be able to handle kind of both types queries that are like everything, kind of like a relational query where it's I want everything about this specific server, maybe. And then you also have a situation where you want like an analytics type query where I want all for every server in my fleet of servers, I want the average like CPU utilization or something. So from a performance perspective, they kind of have to be able to serve both those needs, which makes them architecturally pretty interesting. Big thing for like a data access perspective is it's optimized for high write throughput. Pretty much above all else is that these databases they're built to handle hundreds of thousands, millions of data points being written per minute, per second, up to like nanosecond precision in some cases. So and then the query perspective is often they're also queried based on like a time range. It's like I want every data point within the last 5 minutes, within the last hour, within the last day. So it's got to be optimized to handle those types of queries, and the indexing structure is based around that. Other things, you got built-in features, so like developer productivity features for working with this type of data. And the examples are going to be InfluxDB, Timescale, and QuestDB. So the pros and cons, obviously you get the very fast data ingest and query performance explicitly on stuff that like it's the ingest is important. Just being able to handle the writes is one thing without failing, but also being able to get that index very fast so that within a very short amount of time of actually being written, it's actually accessible via query. Like there's no, you have to wait an hour after it's been ingested before you can actually query it effectively. And then developer productivity, a lot of these out of the box, you get stuff like data retention policies. So maybe you realize that after a week, you don't really need that data anymore. You're just wasting money on storing it. These databases out of the box will allow you to say, for this basically bucket of data, after a week, just delete that data. Everything that's a week old or more, delete it. And you can schedule that and it just happens automatically. There's also a lot of stuff to support like aggregations. So often you'll be doing kind of analytics type workloads where you want to aggregate data, do different stuff with it, maybe downsample it. Um, so again, those are going to be built in, and query language support for a lot of like common kind of stuff for like time series analysis, forecasting, and also just basic aggregations as well. So a lot of it just saves you like the equivalent SQL query would be multiple lines. With these, in a lot of cases, the query languages will give you like a built-in function that you can just get the data you want. Cons are going to be as a kind of trade-off are that like if you want to update or delete specific data points, these databases are not optimized for that. And that's one again one of those like ahead of time for most time series workloads, you're not going to want to be like rewriting history anyway. So you don't want to update like if a sensor says the temperature was this. Generally speaking, you're not going to want to rewrite that anyway. So that's really not a factor, but that is like if you try to use it the wrong way, you're definitely going to see some performance issues trying to delete and update specific data points. It's optimized for deleting large chunks of data at once, like as it ages out. So the use cases, monitoring, observability type stuff, whether it's your software, it can also be monitoring hardware as well. You have IoT applications, a lot of industrial, renewable energy type workloads where they have sensors on their hardware out in the field and they're collecting different types of data. Financial data is another big area. They're probably kind of the pioneers in a lot of cases where they're collecting like a buy happened for this stock at this time. And they're tracking all these events that are happening in the financial markets, and then they're building forecasts or building projections based on that data. So column databases. These are databases where, as the name would imply, it's stored on disk in a column format. And there's a lot of benefits to this for analytics types workloads, and that's what these are used for primarily. It gives you essentially a lot of, because the data types are the same, like an integer or a string, they're all stored together sequentially on disk. You can choose the optimal compression algorithm for each table of data. And you also get, so yeah, I'll cover it. I'll cover that in the next slide. But the examples of an open source one be ClickHouse, and then you have like Amazon, AWS Redshift, and Vertica as some like commercial examples. So the pros are you're going to get way better performance for analytic type queries. You're going to get better data compression by a significant margin because you can choose like different kind of compression algorithms instead of having to go with like a more generalized compression algorithm. You can choose the one that's best for your use case. And then you get like parallel processing. So these databases, they like it's beyond my pay grade when they go into these levels, but they're able to take advantage of CPU architecture to like do parallel processing on the different columns, and you just get a ton of performance gains as a result of that. Downside is that for writing data, because each instead of being together as a row, to update like an entire row of data, there's a big performance hit because you have to access those on disk in different areas. They're not sequentially there. So if you had a situation where you updated an entire row, I think it's something like a 30%. Like they benchmark this across a couple of different column databases. I think it's around a 30% performance hit for like updating an entire row of data. And if you're in a situation where you're accessing like a ton of different columns, you could also end up where you take a performance hit there. Like if you have a like the ideal kind of use case for a column database would be like, I want the average age of our users. So instead of pulling in the entire row of data about the user, you just grab the age column, you run like an average on that, and you get your result back. If you get a situation where you're taking 100 columns from a basically a row, where you're using a lot of different rows together, you're going to kind of lose the benefits of the analytics database and the benefits of breaking those data into individual columns. And so this is an example of ClickHouse's benchmarks. So if you see, it's not like a 10% better situation. It's like hundreds of times better than like a general purpose database for specifically analytics workloads. So you can see here, it's like several hundred times better than Postgres, MySQL, MongoDB. Now, on the flip side, like this is a purely analytics style benchmark. So um, the result is that if you tried to make ClickHouse do a relational type workload, it's really going to struggle as well. So it's not a completely fair comparison, but you can see like if you know you're going to be doing heavy analytics stuff, it's not like a slight benefit. It's orders of magnitudes faster. So column typical kind of use cases for these is analytics, data warehousing, and observability data storage. And here's kind of a case study. So Uber switched from, I think, Elasticsearch to ClickHouse for their logging data. And the result was they were able to get 3 times better compression ratio, 10 times faster query performance. And the result was that their hardware expenses dropped 50%. They're basically able to cut the amount of servers they needed to do the same work in half by taking advantage of this column database. So graph databases, they're used for basically any data set where you know it's highly connected, and you're going to want to be analyzing those connections between data points. That's what the graph databases are designed for. Bigger feature is the specialized query languages that make it much easier compared to like trying to fit SQL type queries to do these type of analysis. They come with built-in stuff that makes it much easier to kind of plan your queries and create them. Big differences between certain types are native versus non-native graph databases. So native graph database will on disk kind of store it in a format so that it's easier to track those relationships on disk, and it's easier to pull data out of disk onto memory and load it back into RAM efficiently, which means you need less, because the performance takes less of a hit, you get better performance. You then have non-native graph databases, which are basically like an abstraction layer where it might pull from like a relational database and then it forms all that data, puts it into memory in a graph structure, and you still kind of get the performance characteristics, but you're probably going to need a lot more RAM for the same workload. And prime open source examples are going to be Neo4j and dgraph. So pros and cons, you're going to get fast queries, constant time queries for a lot of the common graph algorithms, which wouldn't scale well on, like if you try to do the same thing on a relational database or a different type of database, you're not going to get that. Those queries are going to not scale as well. Big features are developer productivity, the query language, built-in algorithms for common kind of graph searches. You get flexible schema like a normal NoSQL database. It's basically like a node. You can think of it kind of like an object where you can just add, like if it's a person object, you can add a name, you can add an age, you can add whatever kind of information you want. You can update that very easily. And another thing is that it also makes it easy to establish these new relationships between the data points. Um, Obvious con is that if you're not working with highly connected data, there's really no reason to use a graph database. So that's one of those things where it's like, know ahead of time what your data's like, your workload, and it's really not a con if you know ahead of time why you're choosing what you're choosing. And here's kind of just a comparison of a same query and SQL up top, and then like in the standard kind of graph query language for Neo4j, which is also becoming standardized, or a big part of standardizing GQL, which is graph query language, which is going to become kind of the industry standard for graph databases. So you can see the SQL query is obviously like almost 3 times as many lines. You have multiple joins going on, which is going to hit performance. And it just doesn't really look and feel natural. Compare that to the graph language, the graph query, where it's like you can see it's okay. You have a person node. You want the person node where the name is Keanu Reeves. They acted in a movie, so you're grabbing all the movies this actor was in, and then you're finding the relationship. Who were the directors of those movies? And then you're counting, and the return value is just the director's name and how many movies they directed that, in this case, Keanu Reeves was the actor. So it's kind of like these relationships, it's much easier to kind of mentally map when it's very just a natural flow, like feels more just mentally easier to put those concepts together. So use cases, anything where you want to be obviously have connected data. Social networks are the obvious one. I think Facebook probably made them the most famous because you can look at who are friends with each other, and then you can do hops between like, okay, this person is friends with this other person, but they're not friends with each other. It might make sense to recommend them. Same thing can be done with like recommendations for e-commerce. So you have different, like if somebody bought this product, we know that both people bought these products, and this other person also brought this, so we can recommend it to this other third person. And you also have fraud detection and kind of like cybersecurity, where you can see that relationships maybe between like payment processing, you can tie together all these different events between all these different people, and you can use that to like automatically kind of look for fraud and different other things like that. So in-memory databases, these are databases where the data is stored entirely in RAM. And a result of this, or a benefit of this, is that they can optimize their data structures without having to worry about any trade-offs for like serializing and deserializing data between disks. So it allows them to use a lot more complicated data structures, which make it very developer-friendly, because you can do lots of cool stuff with your data in memory. And they're able to do that because trying to convert that into something that maps to disk, they just don't even have to worry about it. So the 2 big open source examples are going to be Redis and Memcached. Pros and cons: high performance, and in some cases for like similar workloads, because they don't have to worry about those trade-offs of potentially having to move data to disk. I think I've seen it's like up to 5 times performance boost for similar things. You have low latency because it's in memory. You're never gonna have to worry about going to disk for a certain type of query. It's all right there in RAM. And you get a lot more versatile data types out of the box. Like they can do, like if you've worked with Redis, they have just tons of different types of things they can do with the data in terms of formatting and building it out of the box. Downside, of course, is that RAM is much more expensive than disk, even to this day. It's gotten slightly better, but if you have a huge data set, it's going to be pretty much impossible to try to store that all in disk or all in RAM. And then for large data sets, you're going to have to scale that horizontally, which brings about kind of consistency issues and potentially a number of other kind of things related to that. And in most cases, again, you're going to be using a secondary database for persistence. So using an in-memory database provides benefits, but you're going to have to think about that complexity that's involved with managing multiple databases. So use cases, probably the first and most well-known would just be basic caching of like web content, stuff that's static, or you can just so users aren't hitting your database every time for the same data, you can cache that in memory and just set Redis in front of your database, and it will serve those queries. You can also do real-time applications, anything where you need very fast reads and writes, and some situations like they have support for pub sub, so you can have that data being published and subscribed to different clients, different users. So lots of pretty much anything where you need fast performance, and memory database is going to be a good solution. Search databases. So these are, in a way, kind of a specialized version of a document database. So they're semi-structured, and in some cases, you can also do unstructured data. And they're optimized above all else for kind of text search of your data. So it can be used for logs. It can be used for like auto completion on like an e-commerce store, that sort of thing. So open source examples are going to be Elasticsearch and Millisearch, and also Solr. So top thing is that as a specialized database, you're going to get a lot of productivity gains. They have a lot of built-in like search algorithms, ranking algorithms, different ways to index your data. Some of them just do it automatically. You feed it like raw text data, and it'll just index everything. You don't have to go through the effort of specifying. You're going to get performance and scalability as well out of the box, like you would expect with a standard NoSQL database. Downsides are going to be, because they do a lot of heavy indexing of your text by default, they're going to struggle. Generally, the scaling issues are going to be with regards to writing data. So either you're going to have to replicate those databases a lot, or you're going to have to sacrifice a little bit of indexing to support those write volumes. So use cases, log analysis, autocomplete, like on a website, full text search for your data, and different types of analytics type workloads. Vector databases. So these are designed for basically making any type of data searchable. So they're based around the concept of vector embeddings, which is related to like machine learning, deep learning. And what you can do is you can feed it images, video, text, audio, pretty much any type of data. And what they'll do is they'll generate these vector embeddings, and you can find, you can compare these vector embeddings to each other and find like the distance, the closeness, like it's good for similarity, and determine if like they're the same or how much difference is between them. So the pros is that it's very efficient for vector search. A lot of those, before like these specialized databases, you either had to cobble together a bunch of different open source tools, or you had to just query the you had to keep basically using your machine learning model. With this, you can basically create that model, create those vector embeddings, and then store it in a database and get efficient search with it. You also get hybrid storage, so you don't have to keep it solely in memory. So it's a little bit more affordable to use that hybrid storage. Downside would be it's a very specialized database. So if it's not, if you don't really need these capabilities, it might not be worth the overhead of managing these databases. Use cases are duplicate removal. So if you think like you manage like a service like YouTube or some sort of image service that hosts images, if somebody was spamming you with like the same piece of content, the same image, the same video that's just like killing you in terms of like storing the same data over and over, you could run those before they're uploaded or during the uploading process. You could scan it, say this is like 99% similar to these other ones, and maybe you block the upload. You can also do anomaly detection, or you can do ranking and recommendation engines. So similar to like YouTube, maybe like you see, okay, these videos are similar in these different ways. You can then recommend those videos to people who've watched those similar videos. And new SQL databases. So these databases are basically an attempt to get the best of both worlds, where you get the scalability of a relational or of a non-relational database, but you also get the benefits of consistency and availability of your standard relational databases. So the key one here that kind of inspired them, that gave that kind of the blueprint, was Google Spanner. And then some of these like CockroachDB and these other projects were inspired by that research paper they put out about their own internal tool. And now there's some open source options available. So big bonus, SQL support, so you don't have to learn some new query language. You get horizontal scalability, and they are kind of cloud native. So if you have that type of architecture already, they fit in well with that. Downsides are potential complexity. Like even if it's hidden, even if there's a lot of magic on top, it could bite you if like you never know if things go wrong, and then there's so much magic over what's happening underneath the hood that you can't figure out what's going on. Potential latency because this data is spread across like different regions. Certain queries you could end up going like to a different data center to fulfill a single query. So there's issues with regards to performance guarantees in terms of like latency and stuff like that. There's some SQL limitations, so they might not support every single standard of SQL. So they promise the SQL support, but it's not in all cases like a one-to-one match. And then kind of the opposite of a normal relational database is it's very new technology. So the ecosystem's not entirely there. There's not a lot of people who have experience operating these in production. So you're kind of taking a risk on that aspect of it. So use cases, they promise really to be ideal for anything where you'd want the benefits of the relational along with NoSQL. And some are also kind of promote themselves as being able to support analytics workloads as well. So they're really trying to push as kind of the idea that they're this golden database that can do it all. Whether that turns out to be true, we'll find out, but they do make quite a few promises. So some future trends is we kind of saw this in what we've talked about so far is multimodal databases. So for example, like MariaDB, they have now like column storage extensions. So for certain parts of your data, if you want the benefits, or at least some of the benefits of a dedicated column database, you can get that with like a column kind of table. There's relational graph hybrids where they're not necessarily a native graph database, but they create kind of some usability features on top of your relational like Postgres, and you can get some of the benefits, the usability features of a graph database while also being able to take advantage of your relational database. And relational databases like Postgres have added support for storing like JSON data and other kind of document style formats. So you're not restricted solely to just the table kind of structure. So a lot of these databases are starting to kind of meet in the middle and do different things and not just stay in their dedicated spot. So that's, I think, a trend that's probably going to keep happening. And you can see that especially with those new SQL databases. Another thing is going to be, there's been some research papers about using machine learning to automatically, like dynamically create custom indexes and also just optimize indexes as well. So one research paper from Google and MIT, they created this implementation where by using machine learning to dynamically create indexes, they were able to basically get two to three times faster reads, and the index itself was much smaller in terms of like in-memory requirements. So at the same time, you're not only getting faster performance, but you're also getting cheaper in terms of hardware required. So it's kind of the best of both worlds. And some products now are actually actively using machine learning where they can basically create indexes. They look at that data access pattern in your how basically users are accessing your data, and they can dynamically either recommend and say, hey, do you want to put in this index? Or they can just automatically do it and you get better performance out of the box. Basically, it comes down to the big trends, if you want to boil those down, are usability, making it easier for developers to do different things with their data, and at the same time, use new technology to make databases cheaper to run and faster performance. And all of that basically without the developer having to worry about it. So now we're on to our Q&A section. And again, you can see here some different resources. If you want to learn more about InfluxDB specifically, we have our university, and then we also have like community stuff. We have our Slack and just our website with a lot of resources.
Awesome. Great presentation, Charles. This has been really fascinating. I mean, who knew? There's so much to know about databases. I'm sure the folks on the event today, have been learning a lot, and we've got some great feedback here. Jim out in the audience says this has been really helpful, great information. I also love the InfluxDB University. I think that sounds like a great opportunity for anybody out there who wants to dig deeper into this topic here. While we take audience questions, I'm just going to bring up a poll for everyone out there that says, what additional information would you like about the InfluxData solution? Would you like a data sheet white paper, maybe customer case studies. There's a question out here about that specifically. Pricing, maybe you want to get your own demo, personal demo, or just try it out for yourself. So we encourage your feedback there on that question, and we'll leave it up for you to answer while we take your questions. If you have a question, now is the time to get it in. Let's see, first question I see here, this is an interesting one. Eric is asking, do you have any advice on when I should use a NoSQL database versus a relational database and vice versa? You talked about pros and cons, but can you provide some more examples?
Yeah, it's always going to send. Everybody's kind of got their different workloads, so it's going to be like you can't give a broad swath of advice for any situation. But I guess it always comes down to like relational wise, if you're familiar with it, and like kind of can estimate. Like not everybody's going to be like Facebook or some giant company scale. So in a lot of situations, you like scalability doesn't need to be a huge priority. So if you're familiar with the tool, you can go with that. You don't have to like the benefit of like the horizontal scaling. You might not have to worry about it. So I just say again, it goes back to like how are your users going to access your data? What are your scalability requirements and that sort of thing. So kind of have to just go with the best practices and then fit it for your situation.
Got it. Okay. This is an interesting question from David out there who wants to know if there's any specific database type that has advantages over others in terms of their potential to resist ransomware attacks. Is any one database
Ransomware.
going to be more secure than another one?
Um, I think. I suppose mostly that's going to come down to kind of your application level, making sure people can't get to it. There is stuff like some databases have like built-in encryption at rest, stuff like that. Trying to think, and then there's been multiple cases where like in the early days of the NoSQL databases, for example, the different levels of consistency. Like I know like for crypto specifically, there's a few exchanges that got hit because they're using something like Mongo, and people would basically do like there's different types of skew, like read skew, write skew, and they're able to basically fool the company into giving them a bunch of crypto by taking advantage of that lack of ACID consistency. So at that level, as far as ransomware, though, I think that mostly comes down to kind of your application level.
Got it. Okay. Yeah. Good advice. Paul is asking, what's the best database solution for handling ingestion of high cardinality data, especially if scaling over time is important?
So cardinality wise, big thing like a lot of time series, obviously, like you mentioned over time. Um, time series databases are a good fit there. Some do struggle with cardinality, which is like not to that's a, that can be a deep subject, but like InfluxDB, for example, now is working on and about to release a new storage engine that's column based, so that restricts a lot of or removes a lot of the issues with cardinality. So I just look into like if you want to dive into the documentation of whatever tool or database you're looking at, and look into like how they kind of store that data on disk and how they index that data, and that can help you figure out like where the kind of the bottlenecks are going to be in terms of performance. But I'd say for that type of data, you're going to be looking at like time series or like a more general column based database.
Okay. Okay, good. Edgar is asking if I use one of these specialized database types that you talked about, am I going to need specialized training, or just because I know SQL and basic, database administration, am I going to be able to use one of these specialized databases?
I'd say in most cases, yeah, like a lot of these, especially the open source, obviously, they make it really easy to deploy in different ways. So you can use Docker or whatever tool you're familiar with. A lot of them you can use like some sort of framework to kind of manage it for you. And also, there's tons of managed services. As far as query language, a lot of them do have either their own. Some will have some either like a flavor of SQL or official support for it. But that's just one of those trade-offs you have to think about. That is one of those like where it's like, is the performance benefits for the specialized database worth like potentially having to train part of my team? And that's where I kind of mentioned earlier. It's like you have to factor that in, and like if in a lot of cases or in some cases it's going to be okay, we do need this performance, so it is worth potentially um, taking the time to train people on this new tool.
Got it. Okay. I want to remind everyone about the poll question there on the screen. If you haven't answered that question, now is the time to do it. We're about out of time here on today's webinar. So here's another good question. I know you talked about a little bit of future database trends, but do you have any kind of trends or predictions as to where databases are going in the next few years?
Yeah, I think a big focus beyond like the performance stuff. I talked about like the machine learning, building that into the database. I think it's big on developer productivity. Like I've seen a lot of open source project now, and like at InfluxDB, a big part of our selling point is that it's about the developer, like taking into account your time as a developer, how long it takes you to build these new features. So like part of the platform, really beyond the database, there's the tools around it. How do you collect data? How do you get that data out of the database? The built-in stuff that, as far as working with, in our case, time series data, but for these other tools like graph data, it's a similar concept where it's about like, think about, especially for like a smaller company, um, the speed that you're releasing your product. Like you don't want to have to build a bunch of this stuff yourself that's not critical to your actual product. It's like kind of adjacent to it. So let the database, let this platform handle that stuff, and you can focus on what makes your business basically great at what it does. So I think that's probably another trend that I didn't really mention, is just a lot of these tooling companies, it's becoming about the developer productivity.
Absolutely, yeah. Developers have so little time. Anything that the database and tool set can do, I'm sure is going to be hugely beneficial. This is a good question here. They want to know, when does it make sense to use a time series database instead of a more general purpose database?
I would say um, we have a lot of people who do start with relational and then they migrate over. So if you're familiar with your relational database, you can start off with that, and then once you start running into like scale issues, that's when you think about migrating. Or you can just start. Obviously, we're always happy if somebody just starts off from day one with a time series database. But I'd say it again, it comes down to like, if your primary use case is like some sort of thing where you know users or your internal users are going to be primarily storing time series data, it probably makes sense to start off with that. If, on the other hand, time series is just like one type of data, you can probably try to scale your relational database to start with. And then eventually, if you run into pain points, then you can think about going to a dedicated solution.
Okay, got it. What about, are there any key factors for choosing between which database project to use within a specific category of databases?
Yeah, definitely say like there's open source and closed source solutions. So the benefit of open source is obviously you can start off deploying it yourself. You can kind of have control over it. You don't have to worry about potential like lock-in. Like if you build on a product that's exclusively cloud, you could run into issues where it's like, like, not to trash anybody, but I think Oracle's pretty famous for back in the day. Like a lot of companies kind of got some pretty big bills because once they're there, like they had so much data and they're kind of stuck. So open source kind of at least gives you some option to potentially dodge certain issues. I think everybody's trying to avoid, even now with like the cloud, there's a lot of, you hear all the time stories about vendor lock-in. So open source gives you a little bit of less risk management in that regard. And plus you can just start playing around with it right from day one. Like you don't have to potentially sign up for a bunch of stuff. Like you can download it, run it locally. And it also gives you flexibility, like in architecture, like how you kind of plan your application.
Yeah, I like that. I like that. Good advice. Well, it looks like we're running out of time here. I do want to ask you one last question before we wrap up, and that is, what should folks do to get started with the InfluxDB solution?
Yeah, I'd say that there's that list of resources, but you can start off just downloading it locally. Or we also have our cloud is free to use, free to get started. So you can play around with that as well, whatever's easiest, whatever you're most comfortable with. If you don't want to install anything, you can go with cloud. Or if you're comfortable, just Docker or whatever, downloading the binary, you can do that as well.
Sounds super easy to get started. I do want to remind everyone about the link there in the handouts tab to the InfluxDB cloud. If you go to that link, it says get started for free. And then from there, you can sign up a quick and easy form and try that out for yourself. There's also a lot of excellent resources on that page. comparisons, other case studies, things like that. So make sure that you check out that link there in the handouts tab. This has been a really educational event, Charles. I've learned so much about how to choose the right database for my workloads, and I hope everyone else has as well. Thank you for all your expert content today. And of course, thank you to InfluxData for supporting us on the event today. Check out the resources there on the screen. Those are hyperlinks. If you click on those will take you to InfluxDB University, the InfluxData Slack website, or Influx Days. And of course, try out the solution for yourself. That's the best way to learn, in my opinion. All right, so for our Amazon $300 gift card giveaway on the live event today, the winner is John Law from California. Congratulations, John Law from California. We'll reach out to deliver your gift card, and we'll be reaching out to our best question prize winner as well. Thank you to everyone who joined us on the webinar today. I hope that you learned a lot, and we'll see you next time. Have a great day.